Good morning, everyone. Today I'll be presenting a comprehensive overview of decision tree algorithm as part of our task 8.2c. Working in my name is Siddharth Yadav and my student roll number is 223662644. In this presentation, I'll walk you through what decision trees are, how they are constructed, and evaluated, and demonstrate an example using Python. So let's get started. So, for a decision tree, what first question arises is what is a decision tree? A decision tree is essentially a flowchart like model used to solve classification or regression problem. At each internal node, we test a single attribute. Think of it as asking yes or no question or checking a feature's value. Each outgoing branch represents one of the possible outcome of that test. Finally, each leaf node represents a predicted class level and classification task or predicted real valuable quantity in regression task. In practice, you can imagine starting at the root node. You check one feature of your input, follow the appropriate branch, then check another feature, and so on until you arrive at the leaf, which gives you the final decision. Then, if then structure R1 decision tree are so interpretable compared to many other models. So, to the entropy information gain to decide which features to split on at each node, we need to measure of how impure or disordered a data set is. That measure is called entropy. Mathematically, if a data set contains classes C1, C2 till on Ck with probability P1, P2, and Pk, then entropy is equal to S is equal to summation of I, Kp log of Pi uh, divided by sum, which is entropy is highest when classes are eventually mixed, and zero when all sample belongs to one class. We then compute information gain to decide which feature lowers entropy the most when we split on it. Information gain is simply the difference between the entropy of the parents node and the weighted sum of entropies of each child node after splitting. At each splitting step, we choose the feature with the highest information gain because it most effectively reduces uncertainty about the target label. Uh, tree construction, building a decision tree recursively follows this step, calculating the entropy of the current data set. This measures how mixed the class labels are. For each candidate feature, compute the information gain if we split on that feature, essentially simulating partition the data by each unique feature value. In continuous case, then calculate the resulting entropy of the subset, select the feature that yields the highest information gain, and split the dataset accordingly. This produces one child node for each distinct feature outcomes. Recurse applies step 1 to 3 each child node using one of the subset of data that reaches that child. Continue until the stopping criteria is met. Example, all instance of at node belongs to a single class or each reach a maximum depth of minimum sample count. By repeating this process, the tree grows downwards, partitioning the dataset into increasing pure subset until termination. Then comes the pruning. Even though fully grown trees are perfectly fit or even memorize the training dataset, they often overfit and generalize poorly to new data. Pruning refers to techniques for removing and discouraging overall complex branches that add little predictive power. Pre-pruning, also known as early stopping, halts the growth of the tree before it becomes too complex. For example, you might stop splitting when the node's entropy falls below a threshold or when the subtree would have fewer than a minimum number of samples. You can also impose a maximum depth but require a minimum information gain to split. Post-pruning allows the tree to grow fully first, then attempts to remove branches whose removal does not degrade or actually improves validation performance. One common method is to compare the error on a held-out validation set. If pruning a branch reduces validation error, prune it. Cost complexity pruning is another approach which introduces a penalty tree for complexity in object function. Either way, pruning helps in preventing overfitting by simpling the tree once the redundant split have been identified. So the advantages and disadvantages are interpretability because they mimic human decisions rules. They are easy to visualize and explain. Minimum pre-processing. They handle both numeric and categorical data without needing to run hot encoding, extensive scaling. Disadvantage is like overfitting. With proper pruning, a tree can grow to perfectly fit the training data but perform pruning on unseen samples. Instability. The small variation on training data can lead to very different tree structure. In other words, decision tree have various high variance. So let us come to the implementation in Python. The skit provides a straightforward decision tree classifier or decision tree regressor for classification. So here is a sum of the sample code which is there. So, making prediction to test why prediction is CRF predict. Behind the scene, the classifier runs the recursive predicting logic, calculating entropy and selecting bits until the stopping criteria are met. Note that you can also specify other options such as minimum sample split. So I have a sample return iris dataset to illustrate. Let's consider the classic iris dataset, 150 samples, each with four features: sepal length, sepal width, petal width, and three classes of its iris. We perform a stratified train test with 70-30, ensuring class proportion are preserved. We instantiate a decision tree classifier. After fitting on the training set, we evaluate on the test set in our experiment with max step. We typically see around 96% accuracy. We can also visualize the resulting tree structure using skittle export. And for example, petal length is 2.5 leads to class setosa and so forth. Overall, this example shows quickly a small decision tree can achieve higher precision well separate data. So the performance evaluation, the accuracy is a fraction of correct prediction overall test instances. The precision is especially when classes are imbalanced or when some miscalculation costly than others. We look at the confusion matrix and compute precision. Confusion matrix are tables similar indicating how many samples of each two classes are predicted. As each possible class, it highlights a specific pattern of misclassification. ROC or AUC curve. If we reduce to binary decision problem, use probability estimation. We can plot the receiver optimization characteristic. So taken together, these metrics give a detailed picture both of overall performance and of error and specific in class. They also guide us in tuning hypermeters to improve the analyzation. So let me wrap up with a few final takeaways. Decision trees are powerful inherent interpret mirrors that shine when you need human reachable decision rules. However, overfitting is a common pitfall, so pruning either pre or post and careful hyperparameter tuning, match depth, minimum samples per leaf, etc. are essential to achieve good generalization. Because individual tree can be unstable, they often serve as a base learn and ensemble method, like random forest gradient boosting machine, which combine many trees to reduce variance and boost accuracy. Thank you for your attention. I hope you have a overview helps. You can understand how to construct, evaluate, and use decision tree effectively. I'm happy to take any question. Thank you.